4.1 Radian Degree Measure, first video, Chapter 4. Um, this one's going to be a bit longer. There's a lot of vocabulary things to work out, but bear with me. Hopefully we can jump through it quickly. Remember to pause, write down questions, anything you need to as we go along. What we're going to be looking at today are describing angles using radian measure. Hopefully, all that stuff is review for everybody. Converting between radians and degrees, again, hopefully review. And then linear angular speed, things like that, which is probably new. All right, so let's just focus on vocabulary for a little bit first. We have a couple of new pieces of vocabulary, something like the initial side and the terminal side of an angle. And the initial side is basically where you're going to start. You have a single ray coming off of a vertex, and that initial side starts the angle. Once we start rotating, we rotate, we get to a terminal side over here. So we have two different rays, one that begins the initial side, one that does the terminal side, and in between them, the amount of rotation there is the angle. Okay, so that's just the way and the things that we're going to be using to describe those angles. I mentioned this vertex here. Now we call when that vertex is at the origin, when it's right there, put that in a different color maybe. When it's right there at the origin and the initial side is along the x-axis on the positive, right along here, we call that standard position.
Did you just catch that? It's very, very important.
Okay, and when we look at angles within a coordinate plane and looking at those angles more critically, putting them in a coordinate plane is generally what we're going to do. And then we look at this rotation over to the terminal side again. That we call standard position. Initial side on the positive x-axis, and terminal side can really end up wherever you'd like. Then we have this idea of angles that we are creating. We can create angles in one of two ways. I can rotate, much like I've shown in the past two, in this counterclockwise direction, with the initial again on the positive x-axis because we're in standard form. It goes all the way, and then boom, boom. I have my terminal ray right there, and I have created what's called a positive angle. And that's generally, I think, what most of us are used to dealing with. But we also have this idea of rotating in the clockwise direction. And when we rotate in the clockwise direction, we have our terminal ray down this way. We're looking at what's called a negative angle. And it can get a bit confusing if you're not quite sure which way the rotation is going. So these arrows most often will be accompanying your angle to let you know which direction you should be measuring that angle from. Now when we are looking at these things, most likely the variables we're going to be dealing with in trig are given with alpha, beta, and then we have theta, which most people are used to already. It's just they're Greek letters. The whole idea of trigonometry was developed by Greek mathematicians, so it's just a piece of history that's traveled along. And given this idea, I'm going to use these variables, alpha and beta, to help me illustrate what the idea of coterminal is. All right, so I have two different angles. I have alpha, which is created by going all the way around, doing a positive angle, and landing here in the, not the first, not the second, but the third quadrant. And then I have beta, which is a negative angle, starting again from standard position, and it rotates all the way into, again, the third quadrant. So what we call alpha and beta, because they both end at the same terminal point, we call them coterminal. It's a very
Are you taking notes?
Simplistic name for it. But it can be kind of difficult to tell when two angles are coterminal based upon the numerics. Not when you're looking necessarily at a picture, because it's pretty obvious when you're looking at a picture like this. Okay, well, yeah, they start in the same place and they end in the same place. They're coterminal. But we'll look at another example later where you're trying to solve it mathematically and numerically, which gets a little bit tougher. But coterminal angles come in such a variety of ways, because technically I could create coterminal angles just by, making the positive and making the negative versions. Or, much like in this second example, I have alpha, which is just this small little angle right here. And yeah, I could make beta just by making a negative angle. Do that one in blue. I could make a negative angle that goes from this initial all the way, boom, to the terminal there. And that is a coterminal angle. But in this example here, I'm not doing that. I'm still rotating in the positive direction, but I'm rotating an entire rotation around, boom, all the way. And then I'm doing that exact same angle that alpha was. So basically, it's a full rotation added to the initial angle value that we measured for alpha. All right, so the coterminal angles can be measured by doing a positive version and a negative version that both land in the same place, or they can be measured by doing variations of full rotation. Because another example of a coterminal angle of alpha could have been not just one full rotation, but two full rotations, and then the measure of angle alpha, bringing you again to the same terminal point. And along that same line, it could have been 3 rotations, 4 rotations, 5 rotations, in the positive or the negative direction, as long as it still landed in at this same terminal point. So with that idea, you can kind of conclude that in terms of how many coterminal angles there are with a single one, that number should be infinite, because we can go through as many rotations as we'd like to. Now let's look at radian measure. Okay, most likely everybody's used to degrees, and radians might be something new. They might be something you've heard of. You might have used a couple of different of the more frequent measures. But let's talk a little bit about what radians are. Radians are more a measure. The way that I like to separate, radians and degrees in my mind is radians deal more with arc length and the actual measure of a rotation along a specific arc. Because the formula for one single radian, based upon the idea of arc length, right here we have what's an equation for one single radian, theta. Theta being the variable we use for some angular measure. And what it equals is the arc length that's traveling over the radius of the entire circle. So if we make things simple and say that we're in a unit circle means that the radius is equal to 1. So my formula then becomes theta equals s over 1, and therefore theta would then equal just s. So theta is extremely related instead to arc length rather than the actual angle being measured as we tend to think of degrees. Now, if we think about a full circle, right, and theta is supposed to be equal to the arc length of that circle. Again, we're talking about a unit circle, so the radius is 1. If I were to go all the way around a circle, the arc length of the entire rotation of the circle is essentially its circumference. And circumference equals 2 pi r. Now, if I'm saying that the arc length is equal to the circumference, then that means that s equals 2 pi, and again, we're talking about a unit circle, so r is just 1. So s equals 2 pi. Now, we just also said that in a unit circle, theta, the amount of angular rotation, is equal to the arc length. So an entire full rotation around a unit circle is equal to 2 pi radians. And some of you might already know that, and some of you might have already knew where I was going with that. So a full rotation around a circle of radius 1 is 2 pi radians. And that's where all of the rest of this measurement with radians is going to play off of. And this particular figure right here is not showing in terms of 2 pi, it's showing in terms of kind of decimals. This right here would be 6.28 approximately. Right, we go 1 radian, 2 radians, 3 radians, 4, 5, 6, 6.28, which is just about 2 pi. Kind of just an approximation. And it also shows us that halfway around the circle would be half of 2 pi, or 1 pi. So that's about 3.14 all the way over here. Now let's take the idea of a radian and apply it to this coterminal idea that I talked about a couple of minutes ago. I have a positive angle of 3 pi over 4. Okay, so the radians are going to be expressed mainly using fractions of 2 pi. So this is the first angle.
Important stuff up there.
Like that. The first angle that I'm talking about, this positive angle right here. And it's 3 pi over 4, which brings me right into the second quadrant. And I want to find the coterminal angle right with it. Now I said that there's different ways we can do this. I could do it by just finding the negative angle, which it looks like is what I'm going to be doing, finding this negative angle right here. Or I could do one full rotation around the circle and then land right here again, terminating at the same point. But the terminating at the same point one, that's a little bit easy. It's basically just adding a full rotation, which is adding 2 pi. Let's do the one that's a little bit more complicated, which is finding the negative version. Well, if finding the full rotation was adding 2 pi, finding the negative version is almost just as easy in the same vein. It's subtracting 2 pi. So I take that positive angle 3 pi over 4, I subtract 2 pi from it, and it gives me the remainder of the rotation of the circle right down here. So 3 pi over 4 minus 2 pi, I would have to get a common denominator, which would be a 4. Now I'll make the top an 8. 3 minus 8, negative 5. So my solution here, negative 5 over 4, that's the remaining amount of rotation in a single rotation. So that gives me what my negative angle over here is. Now I have another example where this time we actually start with the negative angle. Alright, so I have negative 2 pi over 3, which is my original angle, and I want to find that coterminal angle, the one that's not negative but instead positive. Alright, so kind of counterintuitively, when you start with a negative angle, you do have to add 2 pi. And if I wanted to get that full rotation that I was talking about in the last one, where we could rotate all the way around negatively and then do the same angle, getting at that terminal angle, when I start with a negative, I would have to subtract 2 pi. Right? It's all about really thinking and being able to process through and understand, does my solution make sense? If I came out with another negative answer right here, I would have to know that it's not going to be the coterminal angle I'm looking for, because I know that my coterminal angle I'm looking for is the positive version. It's supposed to be a positive number. So anyway, let's go into the math of it. I'm gonna add 2 pi, which means when I do that, I need a common denominator that's going to make 3's on the bottom. It's going to make this a 6. Negative 2 over, plus 6 is 4. 4 pi over 3 is my positive solution to the coterminal angle of the given angle, theta. Alright, now let's talk degrees. There's really one connection I want to make between degrees and radians, and that is we don't usually think of degrees as fractional values. But just like an entire circle of radians is comprised of 2 pi radians, an entire rotation of a circle of degrees is comprised of 360 degrees. And we're going to be breaking up radians into these different fractional values, and we're going to be breaking up degrees into these single fractional values. 1 degree is technically 1 over 360, if we think about them that way, but we generally don't. So I want to show that those things are quite similar. It's just different ways of measuring. It's almost too simple that it becomes complicated. So converting between the two, we really just need to set up something that shows us what two things are equal. For example, we just said that 360 degrees was equal to 2 pi radians. So by the same logic, if I don't want 2 pi and I just want to say that pi is equal to something, it would basically be half of 360, which is 180. And that's where these conversions come from. When I divide both sides by 180, I can get pi radians over 180, and that's how I convert from degrees to radians. And if I divide both sides by pi in my next step, I get 180 over pi, which is the way I convert from radians to degrees. So let's see what this looks like when we actually use it. 135 degrees, when I want to convert that into radians, what I'm going to have to do is do a conversion where I have pi over 180, because I want my values I want to cross out, I want those diagonal from each other. So essentially what happens when I multiply across is 135 pi over 180. And now it's just a matter of simplifying the fraction. What number can divide both 135 and 180? And it happens that 45 degrees goes into both of these. On the top, that simplifies to a 3 pi. And on the bottom, that simplifies to a 4. So 3 pi over 4 radians is what I'm looking at. Now for my next one, again, I'm converting the exact same way. Pi over 180. And I chose this conversion because I want degrees and degrees directly diagonal from each other so I can cancel them. And again, when I multiply across, I'm just going to get 540 pi over 180. And when I try to simplify this fraction, I'm looking for what number goes into both 540 and 180. Turns out 180 actually goes into 540 3 different times, so we're looking at 3 pi radians as my solution here. Well, there's my R. Alright, and my last one, I'm looking at a negative angle. Does that change anything at all? No, I'm still converting the exact same way. Pi over 180. And that is equal to, and again I multiply across, so I'm looking at negative 270 over 180. Now I'm looking for a number that goes into both of these, and it turns out that number is 90. 90 goes into 270 3 times, so that becomes 3 pi on the top, still negative. And on the bottom, 90 goes into 180 twice. So my conversion here, a negative 270 degree angle, is negative 3 pi over 2.
Mathed.
Alrighty, now we're looking at this idea of complement and supplement. Hopefully complement and supplement are both very known vocabulary words for everybody. Complement meaning that we're adding up 2 angles to equal 90. Supplement meaning that we're adding up 2 angles to equal 180. So if I'm looking for let's say, complement of 72 degrees, I'm really just looking for what's left over after I do 90 minus 72. And that way I can get my complement right there. And again, if I'm looking for, let's say, the supplement for this one, the supplement of 4 pi over 5. I'm going to do the exact same idea, supplement meaning I'm going from 180, but what is 180 in terms of radians? Because I'm dealing with radians here. That's pi minus 4 pi over 5. And when I have to subtract or add fractions, I need a common denominator, so that's going to be 5 on the bottom there. And 5. So that means that my solution here is going to be pi over 5. Very good. Now let's look at this last idea of linear and angular speed. And I think this is where this section actually becomes a little bit tricky. And this is the one part that becomes like difficult to separate these two vocabulary words. We need to come back first to this formula for a radian, that a specific radian is equal to the arc length over r. If I change that formula just by multiplying both sides by r, I can get this one right here, which is essentially just the equation for arc length, which, again, some of you might have already seen before, some of you might have used before, but it's going to be very important for the next portion of this with linear and angular speed. And what makes them difficult to delineate is that they're very, very similar. One of them, angular speed, talks about how quickly is something rotating. How quickly is it spinning in space? Whereas linear speed asks the question, if something is rotating so much, how fast would it be going if, let's say, like it's a tire. I have a tire that's spinning and spinning and spinning and spinning. What happens when I put it on the ground? How fast does it go in that direction? That's the difference between linear speed and angular speed. Now let's look at this particular example. A circle has a radius 4 inches. Find the length of the arc intercepted by the central angle, 240 degrees. So what is the arc basically from this initial all the way to the terminal when the radius is 4? So this is simply using the equation S equals r theta. And what we need to do first is remember that this equation is derived from this idea of a radian measure. So this equation is specifically designed to use radian values. So I would first need to convert from degrees into radians. So I'm going to have to do over to the side 240, and I'm converting by multiplying by pi over 180. And when I convert, what I get is 4 pi over 3 radians. Cool. So now that I'm able to actually use the formula because I have things in radians, S is going to equal R is 4, and the radians that I have are 4 pi over 3. Now, just multiplying, it's quite simple. I just get 16 pi over 3. And that is how big my arc length is. You know, if I went to approximate this, because I think we're talking inches, it's about 16.7 inches. But that's essentially just using the formula and understanding the formula deals with radians, not degrees. Now let's look at an actual linear speed
Pay
situation.
attention.
The second hand of a clock is 10.2 centimeters long. Okay, so if we're talking about a circle, that's basically the radius. It's giving us a piece of information there just a little bit covertly. Find the linear speed of the tip of the second hand. So I'm looking for linear speed, which means I'm not looking for how quickly this thing rotates around, because technically I know how quickly it rotates around, right? It's a second hand. So it's rotating at a rate of one rotation every 60 seconds. So that would be a pretty simple question to answer. But instead I'm looking for the linear speed. So it's how quickly is this whole thing moving in a linear direction. So what do I need? I need this idea, if I flip back, where linear speed is supposed to be the arc length over time. So it's basically how fast it's going on this arc, how quickly it's moving on this arc. So I don't know the arc length. I need to figure out what the arc length is. And arc length, S, is given by theta times R. And I know R. But do I know theta is the question. So here's what I'm going to do. S equals R, which is 10.2, and then theta. And if I think about what I'm doing here, I'm doing a full rotation. So a full rotation in theta, or in radians, is 2 pi. So that is my theta value. Now the S equals, when I multiply the two, just about 20.4, that's a point, pi. Cool. I'm not completely done yet though, because what I need isn't the arc length. What I need is how quickly it's moving around that arc length. So I need linear speed equals over t, which in this case s is going to be 20.4 pi, and time. How long does it take to make that full arc length, to go completely around? Well, we talked about that in the beginning. A full rotation is 60 seconds. 60. Cool. So now if I do my division here, 60 goes into 20.4 pi, and that's just about 1.07, and we're talking, let's see, centimeters per, and then we talked about 60 seconds. So 1.07 centimeters per second is the linear speed of this hand, the clock. And I actually think that is the end. Make sure that if you have questions, you write them down so we can discuss them all in class. Make sure you do the assigned problems, and I will see you all next time.